All right, so what is a sequence? Well, a sequence is an ordered list of numbers. So what that means is we have a group of numbers and, well, there's an order associated with it. So an example would be something like 1, 5 over 4, 5 over 4 squared, 5 over 4 cubed, and so on. So typically the way that you'll write this is you'll list off some of the terms in the sequence, and you can use a ... to denote the fact that this is going to be continuing indefinitely. So this could be an infinite sequence that extends forever, and you'll use curly braces to enclose the actual numbers in the sequence, which are called terms. Okay? So sequences are ordered lists of numbers. And sequences are actually very useful for describing patterns that we see in the real world. And often, the way that we'll describe that pattern is with a function. So let's denote the nth term in this sequence with a subscript n. So we could call this maybe a1, a2, a3, a4, and so on. And the nth term would be a n. And we could describe this pattern by finding some function such that when I plug in n, I actually get the right number within the sequence. So in this case, there's a very simple rule that can be used to calculate these terms. An is actually just 5/4 raised to the power of n minus 1. And you can see that when you plug in 1 to this formula, you get 5/4 to the 1 minus 1, which is just 5/4 to the 0, so 1. And if you plug in a3, you'll get 5/4 to the 3 minus 1, or 5/4 squared. And that would work for any term within the sequence. Okay, so we can use sequences to describe an ordered list of numbers, and often the pattern can be represented with a simple function. All right, well, let's give this particular sequence some context. Since we're dealing with a pandemic right now, let's suppose that we have a scenario where on day 0, there are 64 cases, 64 new cases of COVID-19. And let's suppose that on each subsequent day, we have 25% more cases than on the previous day. So each day, the number of new cases is 25% higher than the previous. Well, what would that mean? Well, that would mean on day 0, we'll call this A0. Sometimes you'll start a sequence with the index 0. Sometimes you'll start with 1. So on day 0, we have 64 new cases. On day 1, we'll have 25% more, which means we'll have 5/4 as much as we had on the previous day. So we'll have 64 times 5/4. And then on the next day, which we'll call A2, we'll have 5/4 of what we had before. So 64 times 5/4, that was what we had on day 1, and we'll multiply that by 5/4 again to have another 25% increase. And you can see that there's a nice little pattern there. The nth term is just going to be 64 multiplied by 5/4 raised to, well, on day 1 we had 1 factor of 5/4. On day 2 we had 2 factors of 5/4. So on day n it looks like we should have n factors of 5/4. Okay, so the number of new cases can be represented by a sequence, and you can ask lots of questions about that sequence, like, well, what is it approaching? How fast do its values grow? Another question you might want to ask is, what happens if I'm interested not in the number of new cases, but in the number of total cases? And that's a question that relates to what our main goal for this unit is. It relates to infinite series. So we can create another sequence which represents the sum of the terms in this sequence. And so on day 0, we would call, let's call the first term in the sum S0. S0 would be 64. We have 64 cases on day 0. Then on day 1, well, how many cases are we going to have? Well, we're going to have the 64 from the day before, plus we'll have the number of new cases, 64 times 5/4. And then on day 2, we'll have 64 plus 64 times 5/4 plus 64 times 5/4 squared. And you can see this is another sort of sequence, but the way that we calculate the terms in the sequence is not just by the simple formula, but rather we're adding up the terms in our original sequence. And so I won't write down the formula for Sn, but it will be a little more complicated than An. But the main thing to note here is this is a special type of sequence that is generated by adding up the terms in another sequence. And that is what we would call a series. So on the left, An is a sequence, and on the right, Sn is what's called a series. And again, there are lots of questions you can ask. You can ask, well, does the sequence approach something, or does the series approach something? Is there some number that those sums are going to get closer to? We can also ask, well, maybe they don't get closer to something. Does it diverge? Does it go off to infinity? And so what we're going to look at over the next few weeks is how do we actually describe these types of sequences in series? How do we determine if they converge? And if they converge, can we determine what they actually approach? All right, so this is going to involve using some tools from limits. It's going to involve using some tests for convergence. And so we're going to learn a lot about that in the coming weeks. Now, one thing I want to briefly mention is that there's something a little different about these sorts of questions involving limits of sequences than the types of limits that you've seen thus far. So let me scroll down just a little bit here. Normally, when we talk about the limit, say, of 1 over x as x goes to infinity, x is a continuous variable, meaning it takes on any sort of real number. And so we can change x in very, very small increments and see how that affects what this function 1 over x is approaching. Here, when we talk about sequences, I could talk about the limit as n goes to infinity of 1 over n, but we really mean something a little bit different there. When we talk about limits of a sequence, n does not change by some small increment, but rather it's an integer that corresponds to the index of a different term in the sequence. So n only goes up by increments of 1. And so it's not obvious that we can use the same types of limit techniques that we used to study limits like the 1 over x1 that I've shown above to solve these limits that involve sequences. But what we will see is that actually you can apply these sorts of techniques, and there are some theorems and limit laws similar to the ones that you saw in your Calculus 1 courses that will actually help us deal with sequences as well. All right, so that's the end of this video. We'll talk more about this and do some examples in the coming videos.